The trick towards solving these type of problems is to be as cool as a cucumber, and you'll know what I mean when we start solving it. Okay, so a few things to keep in mind. Whenever you're solving these problems, you do want to solve it by component method, and you want to have a defined coordinate system. In other words, you want to define a certain direction as positive, and then logically the opposite way as negative. One of the problems about charges, as you may know, is that if this is a positive charge, you'll notice that up above, the arrow will be pointing upwards. Meanwhile, if you're observing from down here, the vector will be pointing downwards. And the same thing is also true from side to side. All right, and it'll throw off your calculations if you forget which way it points. So instead, we just want to define, in general, upwards as positive and towards the right as positive. And if the vector points the other way around, then we'll define that as negative. Okay, and yes, whenever you're solving these problems, breaking them into their horizontal and vertical components, find out the resultant displacement or the resultant E field intensity by using the Pythagorean theorem, and then the angle using inverse tangent. All right, and that's pretty much what you have to do. Just have to be very careful in your calculations and in your measurements. Okay, so we'll go through this example right here. It may seem straightforward, but there's a few catches you got to watch out for. All right, so what we're trying to do is that we want to figure out, well, where does the E field point here? Does it point, this way, that way, or whatnot? So the direction of the E field, right? Which way does it point? And then after you find out the direction where the E field points, number 2, you decide to place a charge right over here. All right, and depending upon whether this charge is positive or negative, you'll either move in this direction here or may move in the opposite direction. In fact, is there more information here? Yeah, these are the given values. Okay, so given these values over here in this diagram over here, figure out the direction of the E field and find out the corresponding push or the force on a charge if it was placed right on X. Okay. Well, let's get started. Okay, so we're trying to find out the E field that corresponds to this place over here, and it's based upon a superposition of the E fields coming from charge 1. Charge 2 will be negative, so we'll be pointing like so. And charge 3 is positive, so we'll be pointing in such a way. So you'll notice that when we superimpose these on top of each other, we have a vector that looks like that, plus another vector that looks like that, but it's also much further away, and plus another vector that's pointing upwards. All right, so you have to add up all the horizontal components, then add up all the vertical components, and then if we do everything carefully, then we'll get the corresponding answer for what the E field will look like right on this exact spot. Something to keep in mind is that no, the E fields will not be parallel at this point over here, because these are all point sources, and because their vectors just spiral away from it, well, not spiral, but just radiate away from it, you're not going to have a uniform E field. All right, it'll just be the vector sum of them all, and it'll have a weird curvature or twist to it. Okay. All right, so let's just do the careful math and figure out what's going to happen at that test point over there. Okay, so if we take a look at it from the horizontal component perspective, we know that charge number 1 has an impact on it. Charge number 2 has an impact on it. Charge number 3 has no influence in the horizontal component because it's just directly vertically above it. All right, so it only has a vertical influence on the E field, which will look like that at that point over there, and we don't need to worry about anything horizontally. As you may have guessed, this vector over here is probably the easiest to calculate out because it's just the straightforward answer, but this one over here will be quite challenging. Okay, so let's go off and figure out what is the Q, at least in, or not the Q, the E field in the X dimension here. All right, and I know that it kind of gave away the answer over here, but let's just explain what all of this means. Okay, so the E field in the X dimension is equal to the horizontal component from charge number 1 and the horizontal component from charge number 2. So even though, let me just color code this, even though the resultant vector will be pointing like so for the for Q2, this weird angle over here is based upon 2 parts. It's based upon a horizontal component and a vertical component. Okay, so Q2 will be the messy one to calculate out. Q1 isn't going to be too hard. So if we do Q1, well, we know that E field intensity is equal to KQ over R, as you can see right up here. All right, K is 9 to the power of 9, or if you want to be more proper about it, 8.99 to the power of 9 newtons times meter squared per coulomb squared. All right, so we have the value of K, we have the value of Q, and the radial distance, not too bad, 2 centimeters away. Just make sure that you stick with your MKS system. All right, so for meters, kilograms, and seconds. All right, so your distances need to be measured in meters. That's why this 2 centimeters has to be written down as 0.02 meters right here. Okay, so the first one is not too hard to solve. The second one, it does get a bit messier. All right. For one thing, if you take a look at this vector over here, it is pointing towards the left. So if we assume right as positive, then left will be negative. And that's why there's a minus sign over here. These absolute values here is just to get rid of the vector value, because as I said, if you have a charge like so, well, depending upon where you're observing this from, the vector that you're paying attention to will be completely different depending on where you place it. All right, so we don't even care if it's positive or negative anymore. We just need to think about logically, which direction will the vector be pointing based upon our circumstances. Okay, so for the first vector, it will be pointing towards the right. That's why it's kept as a positive value. And the second vector, if you look at the horizontal component, it will be pointing towards the left, and that's why we have this minus sign here. Okay, so the value of K, not too bad. Q, we have it. It's at 2 microcoulombs, and we're not going to worry about the minus sign. But the hard part is the radius. Most of the time, the students by accident use the value of 0.02 meters. All right, but that's just this part over here. We need to take a look at the horizontal, this diagonal component, all right, which is longer than 2 centimeters. All right, and as you can see, because it's part of a right triangle, and that's the hypotenuse, then we just have to do the whole c is equal to a squared plus b squared, all square rooted. All right, and that's why our denominator looks like that. Okay, but that's not the complete correct answer yet. All right, you got to keep in mind that we're only looking at this component of it. So even though we have the radial distance, our E field intensity is based upon the horizontal component. All right. So if we draw a theta, I guess I must have drawn it the other way around. Adjacent, I must have drawn it like this. At least when I calculated it out, it must have been drawn according to that. Okay, those are the components of it. So the theta would have been over here, and we're looking at just the horizontal component. So we're looking at the cosine of our E field. Okay, so we're looking at the cosine of it, just the horizontal component. That's why it's cosine 45. Okay, so it's the cosine of our hypotenuse. All right, carefully calculate that away, and then you'll have an answer which by itself it is meaningless so far. Okay, well, let's continue calculating away. So that's just our horizontal component. We're going to rinse and repeat in the vertical dimension. Once again, just being super careful about our calculations. The first charge has no impact in our vertical component because, again, we're only looking at just this E field. All right, just this particular line of the E field. We're not concerned about the rest because we're curious about what's happening here. All right, so that has no vertical component, just a horizontal component, so that doesn't matter anymore. Q2 does have a vertical component. I assume that I have to draw it like this, just to be consistent with my sine cosine from before. Okay, so this time around we're just paying attention to just this vector here. And since it's going to point downwards, our Q2 will have to be negative. Our Q3, on the other hand, as it's going to be pointing upwards, that will be a positive vector. All right. So how did I list this? So I listed this as E3 first, which is positive, and then E2, as I mentioned, will be negative. E3 will be easier to calculate out, or Q3 will be easier to calculate out, because, again, we're just looking at just this vector over here. We don't need to break it down into its parts. We know that it's going to be 0.02 meters away, so we have it listed right over here. And we know our value of K, which I guess in this case over here I factored out, and there's nothing wrong with that, all right? The first example, you'll see that I wrote down K twice, and the second example, there's nothing wrong with factoring out K, so this is just showing you a different way of solving it, okay? Which is still grammatically correct. Okay, so our Q3 is equal to K, which is 9 to the 9, times Q, which is 4 microcoulombs. It's pointing upwards, so then that's why it remains positive. And the distance away that is away from it is at 0.2 meters, so that part is fine. Okay, the second one's going to be messier. All right, so this guy over here is going to be the messier one, because the K value we have, Q, again, we're not going to pay attention to the minus sign here. All right, that's why we have the absolute value. Instead, just knowing that it's pointing downwards, that's why there's a minus sign right here. Okay, so the minus sign here is intentional, just to tell us that when we calculate it out, we know it's going to be a vector pointing downwards. Okay, so we have our K dealt with, we have our value of Q, and our R is the hypotenuse. All right, so it's not 2 centimeters, but it's that of that triangle here. All right, it's the hypotenuse. So you have to do your whole your a squared and your b squared, and that's what I dealt with right over here to find out the true radial distance. How far are you really away from that test point? Okay, it's not just 2 centimeters away, it's, I guess, 2 root 2 when you calculate it out. Centimeters. And the last thing is that we're only concerned about the vertical component. All right, so if we take our theta over here, and our theta is at 45 degrees, as this, has the height and base of the same length, so it has to be at 45. So as a is opposite 45, we multiply by sine. Okay, and after you calculate it through, you'll get the vertical components. So what do those values mean? All right. Now 10 to the 6 means million, so we know it's going to be a very big value, but this value over here is even bigger. So in other words, vertically you're winning way more than horizontally. So as a result, when you look at the E field, at least through this point over here, it's probably going to look something like this, at least at that point there. Okay, it's going to look rather steep, okay, based upon these values over here. All right, 6 million versus 74 million when you expand out 10 to the 7. All right. Okay, so how do we find out how long that green vector is? Well, we pull out good old Pythagorean theorem. And we do inverse tan to find out the corresponding angle, all right, of a vector that looks something like this. So you sub the values in, crunch it away, and just to cut to the chase, you're going to get that answer there. Okay, 74 meganewtons per coulomb. Okay, 74 million newtons per coulomb, up at a 5-degree angle towards the right, as predicted in this diagram right over here. Okay, so we got to that part so far. So we answered the first part, which is, what is corresponding E field at that test point. And number 2 is, what if we decide to drop a charge right at that test point? How quickly will it accelerate? Okay, so the next part is finding out, the force of the charge acting on it. And we know that F net is equal to ma. And that's how we can find out the acceleration afterwards. Okay, so the force acting on the charge is equal to Q multiplied by the E field. And here's where you just have to think about logically of what's happening. Okay, we have an E field that's pointing diagonal like that. It's kind of like having a positive charge. In other words, the positive charge is winning versus the negative charge. All right, so if we had all these charges reversed, so for example, that was negative and this is positive and this one was negative, then we'll have the same exact answer except that the E field will be pointing in the opposite direction now. Okay. And then that will change, how a charge will respond. So in this case over here, it's effectively behaves like there is one positive charge where its E field was radiating towards the upper right-hand corner. Okay, and you decide to pop in a positive charge. And we know that positive and positive, well, like charges don't like each other, so it's going to repel. So the final answer of whatever this FE is, its direction will also be up 5 degrees to the right. And if you're wondering if this was a negative charge, then it will be pointing downwards 5 degrees towards the left. All right, but it was a positive charge, so we know it's going to be upwards 5 degrees towards the right when we sub it in. I think I already did the calculations for this. Oh, I did it as one big shortcut, but let me just solve this in its points, okay, or as in its parts. So that's equal to 3 times 10 to the negative 6, because that's what micro is, coulombs multiplied by 7.43 times 10 to the 7 newtons per coulomb. And this will tell me the corresponding force. All right, so my force is equal to whatever number that is right here. And since that is the overall force, that does correspond to the F net. All right, because we're only looking at just that one E field and that one charge. So that will be your net force. We're not going to worry about gravity in these problems here. All right, so that's your F net. And we also know that F net is equal to ma. So A is equal to F net divided by the mass. And that's why I had to tell you what the mass was. Once again, watch out. Make sure you stick with MKS units. So you can't use 0.010 grams. You have to use 0.000010 kilograms. And writing out like this, just so I know that in scientific notation, it'll be 1 times 10 to the power of 1, 2, 3, 4, 5, negative 5 kilograms. Okay, so watch out. Make sure you have that substituted in for your mass. I think in my shortcut over here, I kind of just cut to the chase. So I dealt with it right over there. And then it'll get you to your answer. Okay, so it's going to accelerate rather quickly. 22 million meters per second squared. Yeah, it's going to travel rather quickly as it's a very strong E field. All right, it's Yeah, it's in the millions, and you're dealing with a very small mass, so it's going to accelerate rather quickly. All right, and that's how you solve these problems. You just have to be super careful with your calculations. Before we leave, I want to show you the end result of just using the simulation software that I talked about in the previous lesson. Let me just pull out the window. Yeah, this one right over here. All right, so when I use this app over here, what I ended up doing is that I just took the positive charge. I think I dropped 1 up here, and I dropped 4 of them here, just to represent, 4 microcoulombs. Now this is in nanocoulombs over here, but really we're just taking a look at how comparatively how much more intense it is, and your E field field diagram will still look the same. All right, whether if you do it in nanocoulombs like what I did with over here, or if you did it in microcoulombs like in the question, or if it was in some insane huge value like in a coulomb. Right, the overall E field map would look the same. The only difference, hypothetically speaking, is that you just be drawing more E fields, right? Because you want to draw them nice and packed and close together, just to remind the reader that your intensity has increased. That's all. All right. So when they're far apart, the intensity is lower. When they're close together, they've increased. Do the lines really exist? No, they don't exist. All right. We have to use our imagination for these things, or use the simulation software over here to help us visualize what's going on. All right. So I dropped everything in according to its intensity ratio, and if you take a look right over here, you can see that my end result should be pointing somewhere towards the upper right hand corner. All right, I know it's not in high enough resolution to show these smaller parts, and there's no way for me to simulate that unless if I take these points and I place them really far away. All right, so I'll leave that as an exercise for you guys. If you place them much further away, and you just make sure that they're at the the squares of the vertices of a perfect square, like 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Hey, I got to the answer over here, and you can see the end result is still up 5 degrees towards the right. All right, so that's what the E field would look like somewhere up there. So I do encourage for you to use these apps so that you can visualize what the outcome would be, because to do the calculations, as you've seen, we did all that exercise just to find out the corresponding E field right over here. And imagine if you had to sit down and do it for the rest of this. It'll take a very long time to solve, and that's why we use computer simulation software. It speeds things up, and if this software was a bit more I don't know about advanced, but just had a bit more options to it, it could probably even connect these together so you can see the overall curvature of what the E field should look like, as opposed to these point compass needle vectors. In any case, that's it for today's lesson. As for the answers here, the answer key can be found on the textbook answer key website. If you take a look in the description of this YouTube playlist, you'll find where to find that there. As it is copyrighted material, I'll just let you go to that website. You can check it out for yourself. But for the non-copyrighted stuff like Course Pack page 19, questions 8 and 9, here's the answer for question number 8, freeze frame if you need to, and here's the answer for question number 9. Best of luck in your homework, and I'll catch you in the next episode.